For Astronomical Spectroscopy by Brandon Davidson and Zach Foster.
Today we're going to talk about the chemistry behind astronomical spectroscopy and its uses and applications in the world.
It's a common technique used by many astronomers today, and it can be used to determine the chemical compositions of stars and other celestial bodies far across the galaxy. This is done by viewing the unique spectra emitted by different elements in these celestial bodies.
It was first used in 1859 by Gustav Kirchhoff and Robert Bunsen, who was known as the guy who invented the Bunsen burner. They used it to view the flames of different elements that were burned. They discovered that every element has a unique spectra.
In 1885, Edward C. Pickering undertook a huge project of spectral analysis, in which he ended up classifying over 10,000 stars in 13 different spectral types. But then, by 1924, scientist Annie Jump Cannon expanded this list to over 250,000 stars that he had not previously found.
It wasn't until the latter half of the century that the scientific community began to accept the idea of using photographs produced by telescopes and spectrographs. This wasn't initially used because the results were not that good, but they were easy to acquire. Thus, the methods of spectroscopy, the usual methods of spectroscopy, remained dominant.
As you can see here by these graphs, there are three types of spectra that an element or compound can emit. They are continuous spectrum, emission lines, or absorption lines, as you can see down there. Continuous spectra are produced from solids, liquids, and dense gases, which all have very high gas pressures, which is why they emit all wavelengths when heated, which you can see back here, where it covers the entire graph.
Next are emission lines, which are produced by thin gases which have low densities. This means that there are less collisions between the atoms, so the emission lines are representative of specific photons that are emitted when excited atom states in the gas make transitions back to lower levels, which you can see right there where the emission lines are shown on the black background. Next are absorption spectra, which are produced when light passes through a cold dilute gas, where the atoms within the gas absorb at characteristic frequencies, and since the re-emitted light is unlikely to be emitted in the same direction as the absorbed photon, this gives rise to dark lines in the spectrum which represent the absence of light, which you can see on the graph. An important factor in determining the spectra of an element relies on understanding photons. Photons are discrete particles that represent light and can be characterized by wavelength and frequency. It's important to remember that different wavelengths correspond to different colors. At the bottom of the screen you can see the equation for an energy of a photon, which is the energy of the photon equals hv equals hc over lambda, where h represents Planck's constant, c represents the speed of light, v represents speed in meters per second, and lambda represents the wavelength itself.
Another important factor that helps in determining the spectra of an element is atomic structure. As you should know already, electrons in an element are usually confined into orbitals. These positions of electrons within these orbitals determine how the spectra of the element appears when measured on a spectrograph.
The general equation for the Doppler shift is F equals F of V added or subtracted by the V of the observer divided by V subtracted or added by V of the source. This equation for the source moving towards the observer is F of the observed equals V divided by V plus the V of the source times F of the source. The equation for the source moving away from the observer is F of the observed equals V divided by V of the source times F of the source, where F equals frequency and V equals speed in milliseconds.
You can see here by this picture how the Doppler effect works. As the police car approaches this person, you can see it's going faster and the waves are like scrunching up against each other, which would change how they're being perceived by the person in front of it. Well, as it's moving away from the girl behind it, it would make it lower and further apart as the frequency decreases.
Astronomical spectroscopy, though it may not have much use in industry or in the economy, it could be very useful for the continuation of the human race. Overpopulation or lack of resources are both very real problems that we may very soon face, and astronomical spectroscopy could be used in the discovery of other habitable planets or other planets containing useful minerals and such by analyzing their chemical compositions in hope of finding a planet similar to Earth that may sustain life eventually, or it could be used for minerals which could be helpful in businesses and such.
Because of the eventual usefulness which will inevitably come from this, it would be very crucial to increase the funding for this new scientific breakthrough, because astronomical spectroscopy even now is showing very great results, with the chemical composition of over 1,000 exoplanets and hundreds of thousands of stars already discovered. This could be expanded later to help us discover even more, and the resources may be useful for us continuing the human race, as our own planet is destroyed by things such as global warming.
This is true too because several similar solar systems, such as the one we live in ourselves, have also been found as well.